Okay, so we're going to conclude our unit on simple harmonic motion with a brief look at Fourier series. Now, a Fourier series is simply a technique for writing a function as a sum of sine and cosine terms. Now, you've actually already done something like this before because previously you've written functions as a polynomial, i.e. as a sum of x to the n terms. For instance, e to the x, its Taylor series expansion is 1 plus x squared over 2 factorial plus, etc. And the algorithm for finding each of those terms is known. It's just the nth derivative evaluated at the point a. Well, okay, if you're doing a Maclaurin series about 0, then you evaluate it at 0, and you divide by n factorial. And this process actually works. So if you take sine and do its Taylor expansion, you get, this sequence. That's not a minus sign, that's an equals. Equals there. The first term is x, the second term is minus x cubed over 3 factorial, plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial. So there's sort of a sequence of polynomials. You take one, you take two of them, you take three of them, you take four of them. And how do those work? Well, if you look at the graph of the sine function here, which is in black, you see that each iteration gets better. The red line is the first Taylor polynomial. The next one is the third order, and that now starts to follow some of the curvature of the sine function. The next one is the blue one, and now you can see we're getting pretty good. The green one next is starting to build in this next bump on the sine function. So you've already, just with the first one, you've got excellent agreement, within a certain window, but now you're pushing the agreement further and further along. So Taylor series expansions really do work. Well, why do we need another one? Well, you saw that for the Taylor series to follow the sine function, it was actually kind of hard because, it's a periodic thing. It repeats over and over and over again. And sines and cosines are much better at that. So these then, cosine and sine terms, are just very useful when we're dealing with periodic phenomena. And periodic things come up a lot in physics. So Fourier series are useful. So the coefficients for the Taylor expansion involve the nth derivative over n factorial. What are the coefficients for the Fourier series expansion? Well, it turns out those come from integration. So if you're trying to take a function f and write its Fourier series, you just integrate it with multiplied by each of the cosine terms. So cosine 0t, cosine 1t, cosine 2t, cosine 3t, integrating with f over the interval minus t to t, and then you divide by t. Now, t is the periodicity of the function f, and we will be dealing with functions that are just periodic on the interval minus pi to pi. So actually not pi, but 2 pi will be the period of our functions. So if the function happens to be an even function, then all of the b coefficients are going to be 0. Because for an even function, if you're evaluating it relative to sine, which is how we find the bn's, then on the negative side of the interval, from negative t to 0, this is going to be the same in both cases. Same value, because it doesn't matter for this function because it's even whether you're on the negative side or the positive side. But these two will be opposites of each other because sine is an odd function. So you end up with this integral just canceling this one out. And there's a proof of that in the notes. But it's helpful for us because we can see, okay, if it's an even function, then the expansion's not going to have, the Fourier series expansion is not going to have any of the bn's in it. It's just all the an's. Similarly, if the function's odd, then you won't have any of the an's in it. So let's do a Fourier expansion. Let's do the Fourier expansion for a square root function. So here we see the function is from minus pi up to pi. So that's a period of 2 pi. And it's 0, and then it's 1, and then it's 0 again. So it's an even function because it's symmetric about the y-axis, and that means the bn's will be 0. let's find the an. So we start with a0. a0 has a slightly different definition. We integrate the function from minus pi to pi, okay, times just 1, which is cosine of 0, I suppose, and then you divide by 1 over 2 pi. Now, this is a pretty easy function to integrate because you're just going to be integrating from minus pi by 2 to pi over 2 because it's 0 everywhere else. And then you're just integrating 1 dt. So this just gives you pi over 2 minus pi over 2, which is just pi, divided by 2 pi, so that equals a half. So that's the first term in the Fourier expansion. Next, let's get the a1 term. So now we're integrating with respect to cosine 1t. Well, again, integrating from minus pi to pi, it's 0 everywhere, but from minus pi over 2 to pi over 2. And there the function is just 1. So we just end up integrating cosine over that. Now the antiderivative of cosine is sine. But then we've got to go from minus pi by 2 to pi by 2. So we get 1 over pi. It's the sine of pi over 2, which is 1, minus the sine of negative pi over 2, which is minus 1. So we get 2 over pi for that next Fourier coefficient. We'll do a couple more. Next, the a2 coefficient, we're integrating cos 2t. Well, once again, that integral is 0 except between minus pi over 2 and positive pi over 2. And then it's 1 times cos 2t. So to integrate that, we need a factor of 2 here, and I balance that with a 2 out in front. So it's now 1 over 2 pi. This is cos of u du, so that will be sine of u. And I've got to evaluate that from minus pi over 2 up to pi over 2. Well, now the sine of 2 pi over 2 is the sine of pi, that's 0. And this is the sine of minus pi, which is also 0. So the a2 coefficient vanishes. And in fact, all of the even a's will vanish, because if this is cos 4t, then it'll be sine 4t over 4 pi. And this will be 4 times this, and 4 times this is 2 pi, and the sine of 2 pi is again 0. So just with a quick hand-waving proof, we say, okay, all of the even a's are 0. Let's do one more of the odd ones, just to see if we can identify a pattern. Again, the integral only contributes between minus pi over 2 and pi, where it's 1 cos of 3t. So we set up the u du by putting a 3 there and a 3 in front. This is now cos u du, which is sine u. We've got to put in the limits. Which we do. So this is the sine of 3 pi over 2, which is minus 1. And this is the sine of negative 3 pi over 2. Well, negative 3 pi over 2 puts us up here. So the sine function is again positive. So that's minus 2 over 3 pi. So what we see then is that the a0 term is present, but all the other even a terms are absent, so a2 and a4, etc. And then the a1 and a3 terms, all the odd terms are present there, but the sign alternates. So we expect that for the fifth term, it's going to be 2 over 5 pi positive. And then for the next term, it's going to be 2 over 7 pi negative, because that's the pattern that we saw there. Now you can do that by integrating cos nt where n is odd. But I think we've established it enough at this point. Okay, so now just to see if this actually works. So remember, our square function was like this, right? It looked like that. Just to see how well this works, I only took the first 4 terms, right? So 1, 2, 3, 4. maybe, yeah, I think I cut it off there and I graphed it. Well, that's phenomenal success, right? With a periodic function, we're already getting quite close to our square wave. So Fourier series work really well. Now, why are we mentioning it here on this unit in simple harmonic motion? Well, partly so that you see it. It may come up later in the course, but also partly because we, in our previous class, for our forced harmonic oscillator, said, okay, we're just going to take cosine because that works in general. Now, the reason it works in general is if you've got some other forcing function, say like a square wave forcing function, then you can write that square wave forcing function as a sum of cosine terms, a sum of cosine forcings. And that means your solution, if you have a square wave forcing function, for the motion of the particle will be a sum of the things we had before, where each of these amplitudes, right, the amplitude of each frequency term is the coefficients in the Fourier expansion. So if we had this as our forcing function, then what we're saying is that's just a half, which is a constant. Then it's 2 over pi times cosine t. And so we know then this will be the F naught, and this omega forced is just 1. And then the next term up was minus 2 over 3 pi. So this should be negative here for the 3 and negative for the 7. Yeah. So then the F naught's minus 2/3, and this was cosine 3t, so the omega forced was 3 in that case. So any forcing function can be written as a sum of cosine terms, and therefore for your solution, you could just sum up the solution like we had earlier. And that's useful. That means that what we did last time was general. Now we're going to start in class by getting you to do a Fourier series, your very first one, just by finding the coefficients like this. And then we're going to spend some work time on the simple harmonic oscillator, the damped harmonic oscillator, and the forced harmonic oscillator.